Okay, so what we want to take a look at then next is we want to start getting into Newton's laws. When we're looking at Newton's first law, there's a couple of things we have to understand before we can even go into Newton's law, and that is inertia. So we need to understand what is inertia. And a very, very good example of what we can do here is if we put a glass of water or something on top of a table, if we put a piece of paper under it, and we rip that piece of paper out, the glass will stay where it is. Now, inertia is the property of matter which maintains an object's state of rest or its motion in a straight line, and we call this inertia. So, the inertia of an object is the tendency of the object to resist a change in its state of rest or of constant velocity in a straight line. Inertia is measured in kilograms. The beaker remains at rest since the force due to friction between the paper and the beaker does not overcome the inertia of the beaker. So, first, very important thing, a force is required to change the motion of an object. This means that the object resists a change in their motion. Now, the resistance to the change in motion of an object is known as inertia. The bigger the mass of an object, the bigger its inertia. The greater the inertia, the more difficult it is to accelerate the object and the harder it is to stop it moving or change its direction of motion. Now, it's very, very important to understand that we can use a little example here at the bottom of the baby and the baby carrier. If the baby and the baby seat are not properly strapped in, the baby will continue to move forward as a result of its inertia when the brakes are applied sharply by the driver. Another way to look at it is if we talk about, let's say, for instance, comparing something like me throwing a tennis ball at you, which is easy to catch and to stop. But if we do the same experiment and I throw a bowling ball at you, it's going to knock you over because of the fact that the bowling ball has got a much larger mass and therefore inertia. It takes a lot more force to actually stop this object. So what is the relationship between inertia and mass then? Mass is the amount of matter contained by an object and is dependent on the number of atoms and their size. So it's the amount of stuff you're made of. Inertia is the tendency to resist change in an object's motion. Both mass and inertia are scalar quantities and are measured in kilogram. They are equal to one another. A box having a mass of 5 kilogram also has an inertia of 5 kilogram. The equal arms balance would use to measure the mass of an object. However, the inertia would be measured by establishing the acceleration an object would have when a certain force is applied to the object. So Newton's first law of motion. It tells us that an object continues in the state of rest or uniform velocity unless it is acted on by an unbalanced force. Now, very, very, very important, guys. This definition, you write it exactly the way it is here. If you leave out rest or you leave out constant velocity, we don't mark it correct. Now, what does this definition tell us? It tells us that, 1, the object has no forces acting on it, or the forces acting on it are balanced, and the object will remain at rest forever. Or, if the object is moving and no resultant force acts in on it, it will continue to move in a straight line forever. Or, if the object moves at a constant speed, the resultant force on the object will be 0. Now, however, if the resultant force acts on the object, it will accelerate in the direction of that resultant force. So basically, as soon as you see there is a resultant force, we're no longer dealing with Newton's first law, but then we will be dealing with Newton's second law of motion. So let's take the example of we have a car. If the car is stationary, 2 important forces are working on it. And you can try to name them here. So, ask yourself, does the car have mass? Yes. So it will have a force due to gravity. And is the car touching a surface? Yes. So there will be a normal force. What if the car is moving at a constant velocity? Then 4 important forces are acting in this situation. Again, we know there's a force due to gravity. We know there's a normal force. We know there's an applied force of the car's motor accelerating the car forward. And because it's moving at a constant velocity, that will mean that the frictional force in the opposite direction will have to cancel out the applied force. So which forces are balanced here? Now here we know in both cases the force due to gravity balances out the normal force, and in the second case the applied force is balanced out by the frictional force. Now, for Newton's first law, there should be one or two or more pairs of balanced forces acting on the object. Two, the balanced forces only act on one object. Balanced forces on one object will cause the object to remain at rest or move with a constant velocity in a straight line. Now, what does this mean? Balanced and resultant forces. Let's take again, we have an object sitting on a table. And because it's sitting on the table, we know it's going to be experiencing a force due to gravity, but also a normal force in the upwards direction. If we take our block and we still have our force due to gravity and our normal force, but we apply a force of 2 Newton on it to the right, and it's experiencing friction of 2 Newton to the left, then we know that again, the resultant force is 0, therefore the object does not move. What if the object is moving? Well, if the object is already moving, then we know it will still experience its force due to gravity and its normal force because it's in contact with the surface for the normal force and because it's got a mass for the force due to gravity. If we apply a 3 Newton force to the right on it, and it experiences a friction of 3 Newton on it, but the box is moving at a constant velocity to the right, we know that the net force is still 0, therefore still first law. And then what if there is a resultant force? So we have the force due to gravity and the normal force, applied force of 4 Newton to the right, and a frictional force of 3 Newton to the left. Then we know there will be a resultant force because 4 plus negative 3 gives us 1, and that would mean there's a net force of 1 Newton to the right. And in this case, we will be dealing with Newton's second law of motion. Okay, so a very good example that we can look at is always space with Newton's laws. So the shuttle Atlantis is orbiting the Earth. Discuss and explain the following question. So, are the engines running? What forces are there on the shuttle? And what happens when the shuttle re-enters the atmosphere? Okay, so you can pause it here and you can think about the answers and then just play once you are done. So, firstly, are the engines running? Now, this is very important because think for yourself, the shuttle is in space, so firstly, there is no friction. So that means that an object moving at a certain velocity will continue to do so. So there is no need for a resultant force on the space shuttle in its forward motion. So no, the engines will not be running because it's just continuously moving forward in a straight line orbiting the Earth. What forces are there on the shuttle? Now, because the shuttle is still in space, it will experience a force due to gravity. And this force due to gravity will be equal and opposite, meaning the shuttle is attracted to the Earth and the Earth is attracted to the shuttle, but these two balance each other out. What happens when the shuttle re-enters the atmosphere? Now, as soon as the shuttle re-enters the atmosphere, it starts experiencing the full force due to gravity of the Earth, which pulls it towards the Earth, accelerating at 9.8 meters per second. And then we're not dealing with Newton's first law anymore, but we're dealing with Newton's second law. Now, very important thing with anything in space, when we are talking about space, we know there's nothing. There's no matter, there's no friction. So anything moving in space will just continue to do so because there's nothing trying to stop it.